Welcome everyone to this week's Western Hemisphere Virtual Symplectic Seminar. We're very happy to have Chindu Mohanakumar speaking about coherent orientations of DGA maps associated to exact Lagrangian cobordisms.
Okay, I'm going to go ahead and share my screen. All right, so we have the Chekanov-Eliashberg functor. We're starting with Lagrangian. So we have lambda sitting inside of the setting that we're going to be talking about. The particular contact manifold is R3, equipped with the standard contact form dzy minus y dx. And so this is a Lagrangian link. I.e. a link such that the tangent bundle is contained in the kernel of this form alpha. And now we have that dz in this case is the ray vector field. Okay, so now, associated to this, we can just have a category ledge. So the objects of this category are just Lagrangian links, and whose morphisms are exact Lagrangian cobordisms. So let's recall what that is. So we have the symplectization. So R cross R3 equipped with the symplectic form D of e to the t alpha. We have for a big positive number t, so t bigger than 0, we have that lambda plus is sitting up here. And then negative t, sorry, could you say that again?
Oh my God, I'm sorry, I was off, I just was coughing, sorry.
Oh, sorry. Yeah, okay, no problem. So we have lambda minus down here. And we have something going on in the middle. Yeah, no problem. Okay, and then above T, we sort of have this cylindrical end, right? So this is supposed to sort of mimic T to infinity cross lambda plus. Lambda plus. Let's see if I can convince the whiteboard to work with me. So lambda plus. Okay. So I guess precisely what you should say is that L intersect T to infinity cross R3 is somehow equal to T to infinity cross lambda plus. And then down here we have a similar sort of cylindrical end. So negative infinity to negative t cross lambda minus. So, and moreover, there exists a function from, so this thing, we'll call this L. There's a function from L to R such that e to the t alpha restricted to L is equal to df. Moreover, f takes on potentially different constant values on each cylindrical end respectively. And those do indeed have to be like constant. They can't just be locally constant. Okay. Okay, cool. So, great. So we have a functor, CE, going from this category consisting of Legendrian links with morphisms, exact Lagrangian cobordisms, to DGA, which is the homotopy category of initial DGAs with morphisms, chain homotopy classes of DGA maps. Okay. And so describing what this functor is, we have that CE of lambda is a DGA generated by Rabe chords we have that these Rabe chords. So to remind you what a Rabe chord is, these are just trajectories of the Rabe vector field with endpoints on lambda. And so these Rabe chords carry Z-mod 2 grading. And this grading can be upgraded to Z. And the differential counts pseudo holomorphic curves. So pseudo holomorphic disks with boundary punctures of the following form. So we have sort of like I'll write P, Q1, Q2, and then all the way up to QM. And so this is a disk with M+1 boundary punctures and one distinguished positive puncture. And we're mapping this to the symplectization. And this just consists of R cross lambda now. And this is the same symplectization as before, R cross R3, equipped with D of E to the T alpha. And it counts pseudo-holomorphic disks of sort of consisting of A at the top, and then B1 through BM in the bottom. So. Can sort of follow the color coding there. And so here we have that the limit as x approaches P of U of x equals A, limit as x approaches Qi of U of x is Bi. And then we have, we can consider a differential now. So del of A is the sum over all things where the dimension is of this moduli space is 1. And the reason we're considering dimension to be 1 is because we have this translational R direction that we can mod out by. And it's the cardinality of such things B1 through B. And, you know, we can sort of determine this count to be Z mod 2 for now, and I'll be talking about how it was upgraded to a Z thing. Okay, so that's a differential. And so what we have is now lambda, this CE, CE, so okay, lambda minus, CE of lambda minus. We consider the cobordism sigma to be going from lambda minus to lambda plus. So this is like a contravariant function. So CE. This goes to CE lambda plus. And then we have what we're now going to talk about, which is phi. And what we just discussed were the differential, which was del minus and del plus. Now we're going to discuss phi. So phi is a DGA map associated to an exact Lagrangian cobordism. It's a count of disks of a similar form. It's basically going to be the same, except this time we don't have that R translation. So the dimension of this moduli space is actually going to be 0. So they're going to be, our rigid disks are going to be precisely those of index 0. So now we have this going to a cobordism. So lambda plus is not necessarily the same as what's on the bottom. And then we have some disk of this form. And maybe I won't write what the DGA map is, but it's something, it's basically exactly the same thing. So now I'm taking the dimension of that moduli space down at the bottom to be 1. So it's a different of, okay, actually I will write it. Phi of A then is some overall things dimension A B1 through Bm equals 0. Count of this thing, B1 through B. Now A is in CE of lambda plus, and B1 through Bm is in CE of lambda minus. Okay, are there any questions so far on what I've talked about? Okay, cool. Okay, great. So now let's talk about the Lagrangian projection, because the Lagrangian projection is the place where we're going to be able to talk about orienting stuff. Okay, so Chekanov-Eliashberg DGA in the Lagrangian projection. Okay, so actually that statement's not entirely true. You can orient stuff in the symplectization, but the way it's done in the literature was through the Lagrangian projection, and then it was shown in later work that, okay, under the natural correspondence of disks between the symplectization picture and the Lagrangian projection picture, this correspondence can be upgraded to Z coefficients. So it's not immediate that one goes to another. There's something to show there, but but it does. Okay, so Lagrangian projection. Lagrangian projection is basically just looking at the first two coordinates. You're taking R3 equipped with alpha, and you're sending it down to R2 equipped with its standard symplectic form, dx wedge dy. Okay, so by work of Etnyre and Sabloff, it turns out that the count of holomorphic disks okay, so this is what I'm about to say isn't entirely precise. It's more so it's like, you know, all of the extra things you have to add. Rigid counts of holomorphic disks which appear in the definition of the differential are in a one-to-one correspondence with orientation preserving immersions of the following form. So D2 minus a certain number of, so minus the same number of boundary punctures. Boundary of that. Being sent to R2 and the boundary being mapped to Lagrangian projection. So now you can see that the Rabe direction is del Z. So under this Lagrangian projection, the Rabe chords are now being sent to double points. So now we have that punctures are sent to double points. Pipeline. Okay. Furthermore, ENS also, so that's these guys, ENS. They also combinatorially upgrade the differential to Z coefficients using the shading rule. So let's talk about what that shading rule is. So here I have an evenly graded double point. And here I have an oddly graded double point. I haven't told you how these Rabe chords are graded yet, but take it on faith that this is an evenly graded Rabe chord and that's an oddly graded Rabe chord. And the arrows that I drew are determined by the orientation, an a priori orientation that I put on my Legendrian. Of course, whether these chords are even or odd doesn't depend on the orientation. You know, I could flip both around and it would still be even and odd. But yeah, okay, so I have this shading that I then put on the even chords. And basically, the idea is that anything, oops. anything that has a shaded quadrant is hit with a negative sign. So let's see what I mean in an example. So I have this. So for instance, if I wanted to look at the holomorphic disks here, I can see, for instance, a holomorphic disk here. I can see a holomorphic disk here. So all of these are immersed. So this second one here would have a negative puncture of B1. I also have one that has negative punctures of B1, B2, and B3, for instance. I have this one. Okay. So, but now when I endow this diagram with the shading rule, I get the following on the differential. So D, okay. So I'm actually also going to add a little base. Ooh. Oops, accidentally erased that. Still erasing it. Okay, so there. So I'm actually going to add a little base point here. This is what I mentioned before is necessary to have a Z grading. In this case, I have that del A1 because none of these holomorphic disks have any shaded quadrant. They all just have a positive sign. So I have a T given by that right lobe. Then I have a plus B1. I have another disk that only has negative puncture of B3, and I have a third disk B1, B2, B3, or I guess a fourth disk, B1, B2, B3. But what about differential of A2? So we still have this holomorphic disk, which gives us 1. But now I have, for instance, this holomorphic disk, which has one corner at B1, and that quadrant that it hits is shaded. So I get minus B1, minus B3, and then minus B3, B2, B1. Because I'm going counterclockwise. Oh, wait, that's clockwise, counterclockwise. Yeah. Okay. Now, okay, all of this was combinatorial, which basically meant that you start from del squared equals 0 and you work backwards, right? So combinatorially, if you want to show that something, that a shading rule upgrades to Z coefficients, is you start with del squared equals 0, or you start with whatever relation you want, and you move backwards, and then you prove that this combinatorial thing actually gives you the desired master equations, okay? On the other hand, the analytic strategy bakes del squared into 0 equals 0 into the recipe of coming up with the signs. And so I'm going to describe what I mean by an analytic strategy. But first, let me just say that Ekholm, Etnyre, Sullivan showed that the shading rule can be obtained analytically as well. Okay, so let me talk about what I mean by that. So let me first start with. Okay, so this is from Ekholm, Etnyre, Sullivan, EES. So with an a priori set of basic orientation choices. So this is orientation of Rn. Orientation of C, and orientations of determinant lines, capping operators, which I'll tell you what that means, hopefully. But there exists analytically determined orientations of our moduli spaces. Which give us precisely the shading. Okay. Let me stop here and ask for questions. Are there any questions so far? Okay, cool. Okay. So now we get.
I had a quick question just to make sure I understand the previous slide.
Let me go to that to the previous. So, oh, is that the previous slide?
So punctures go to double points. This is in the projection that they go to the double points.
Mm-hmm.
Okay.
Yeah.
Right.
So sorry. So did you say T was? So T, the T base variable is needed to upgrade the grading of the Rabe chords. It's not about the count of the differential. It's about the grading of the Rabe chords, upgrading that to Z. Okay. Yeah, but Catherine, going back to your question, so we have, for instance, like this disk right here would be a one puncture disk mapped into the Lagrangian projection. And this puncture P would be being sent to this double point A1.
I see. Okay.
Yeah.
That makes sense. Thank you.
Okay, cool. Okay. All right. So now let me talk about the main result, which is that you can also do this for cobordisms. Okay, so let's consider the following diagram. And this is a local picture that I'm about to draw, but it's in the Lagrangian projection. So I have something looking like this. A1, A2. These two, so you can see here that I have a Reidemeister move. I just pulled the bottom strand over the top strand. And here I have another Reidemeister move. I pulled the top strand over the bottom strand. These are called, this procedure is called a mini dip. And something I kind of want to emphasize is that this is a superficial thing. So these are here to help localize the DGA map. It helps localize the DGA map with Z mod 2 coefficients. It basically just reduces the number of holomorphic disks you have to care about. So outside of sort of like the box where the cobordism is happening, everything is just a trivial strip. And now by performing these mini dips around where the cobordism is about to happen, I get to even localize those holomorphic disks to a very understandable set of things. So basically, okay, so my cobordism is the following. So this is lambda plus. So technically my cobordism is going to it. And then at the other end is this. Okay. So my cobordism is just adding a strip that looks like this. Okay, so that's how I get from lambda minus to lambda plus. And I'm going to add 2 more base points here. These are really just variables to help us keep track of homology coefficients. But they're not really the centerpiece of what we're about to talk about. So you don't need to care too much about that. Okay, and moreover, to sort of emphasize what I was saying about these mini dips being superficial, so this is sort of the content of Casals-Ing appendix is that can obtain full formula from mini dip formula. And the full formula is a little bit more complicated, but I'm about to tell you what the mini dip formula is. Okay, so you can really just think of these mini dips as a convenient thing for me to get that formula, and then you can derive the full thing later on. Okay, so theorem. If we choose the same basic orientation choices as EES, and the reason that that's important is because I want this to be a chain map with respect to the differential that EES constructed. I want this to be a chain map that intertwines the differential determined by the shading rule. So I don't want it to just be a random chain map that interacts with another random Z lifted differential. So the basic orientations have to be the same. So in this case, our DGA map with homology coefficients is the following. So B of A is S. So this represents the basic disk, which if I look back here, it's the basic disk that has a top Rabe chord going to here, to this puncture, and then it sort of closes out as soon as we get to this middle point where the 2 strands are hitting one another. So it sort of looks like this. So okay, maybe a better way to draw it is if I have like that, that's basic disk. Okay. All right. So so this corresponds to the basic disk. I also have one punctured discs coming out of A1 and A2, but only A1 and A2 because of these mini dips. So that's a helpful part of the mini dip, is that I know exactly what the holomorphic discs are coming out. I have one trivial strip coming out of A1. And then I have another one punctured disc, and this is now being endowed with a negative sign. So minus S inverse. A2 minus S inverse. And then all other Rabe chords are being sent to AI. Maybe I'll give you a little bit of history before this. So Casals and Ng, the paper I mentioned earlier, they were able to get, so they determined the above as a certain type. I won't tell you what this is, but as a link automorphism class. So they were able to basically get that the DGA map induced by the saddle cobordism was the above formula up to what is called a link automorphism. So they weren't able to get it precisely, but that is because they use combinatorial methods, which is starting from the chain map and going backwards. We instead use the analytic methods of EES, which gives us then a precise formula. Moreover, so let's recall that a decomposable exact Lagrangian cobordism, I suppose I should say without maximums. So I'm not thinking about caps, for instance. But decomposable exact Lagrangian cobordisms are those which can be decomposed into the three Reidemeister moves. And saddle moves. These have been fully lifted to Z coefficients using a method by Kalman. And now we have it for saddle moves as well. So this theorem now completes lifts to Z coefficients of all decomposable exact Lagrangian cobordisms. Because recall that the mini dip picture implies the full formula for an exact Lagrangian cobordism. Okay, and moreover, it's still an open conjecture whether any exact Lagrangian cobordism isn't decomposable, or it's still an open question whether there's any non-decomposable exact Lagrangian cobordism. So this is a very large class of exact Lagrangian cobordisms, at the very least, if not all of them. So, okay, so great. I don't think I have much time left, but maybe with my last couple minutes, I can tell you how we obtain these analytical signs. This is sort of like starts from a classical thing and then builds up a little bit more with work by EES and Karlsson. So how to get analytic signs. Okay, so, okay, 1, choose a spin structure. on your exact Lagrangian coordinate. Now, I want to point out that one of the most, a question that has a lot of interest in the theory of Legendrian links right now is what sort of fillings are on Legendrian links. And so because we care about, so a filling is just a cobordism whose bottom end is the null set. So it's filled. So it looks like this. It's a cobordism like that. And so because of that, the natural spin structure we should think of is those whose on the boundary components extends to the disk. So the null coordinate spin structure. So since we care about fillings, null coordinate. So for example, if I have a pair of pants, this would extend to the disk on each component. So extends, so be the unique spin structure, which extends to S2 on the pair of pants. So for example, okay, 2, choose 0 skeleton to be endpoints of all RAID chords. As well as those base points I mentioned before, TJ and those SJ plus or minus ones. So so then now a spin structure is equivalent to trivialization of a potentially stabilized tangent bundle on a 1 skeleton, which extends to the 2 skeleton. Okay, so so for example, something like, so if I had that basic disk from before. Oh wait, actually let me just show you what the 1 skeleton is, and I haven't told you the next step. So something like this be a perfectly good 1 skeleton. Okay, and then we want to homotope boundary of our holomorphic disk. So I see I'm at time. Is it okay if I talk for maybe like 3 or 4 more minutes?
Yeah, go ahead.
Okay. Homotope the boundary of our disk rel the 0 skeleton, so rel the RAID chord endpoints, onto the 1 skeleton. This gives a trivialization of the tangent bundle, so of U star TL on the boundary. And perhaps a question you have is like, does this depend on the choice of homotopy onto the 1 skeleton? And the answer is no, because of the fact that we have a spin structure. So if we homotope one way onto the 1 skeleton or another way onto the 1 skeleton, you can simplistically approximate what connects those 2 approximations by a 2 cell or by a number of 2 cells. and the spin structure is supposed to extend across that. So at the very least, these trivializations you get would be homotopic rel the endpoints, no matter what way you homotop it onto the one skeleton. Now we attach capping operators so these are RP, R and E, RPO. So this is supposed to be positive even, negative even, positive odd, negative odd. So these are maps from the one punctured disk to U of n. And this closes up our holomorphic disk. So at a positive even chord, for instance, we would attach a positive even capping operator. And so at a, for instance, like a 3 punctured disk, we would be attaching 3 capping disks to get a closed disk that has a trivialization on it. And maybe I'll just say the last parts. By Fukaya, Ohta, Ono, a closed disk equipped with a trivialization of its Lagrangian boundary condition has a canonical orientation of the associated determinant line. So it's really this trivialization that we were aiming to get. That gives us a canonical orientation. And then by a certain exact sequence given by this gluing, it then induces an orientation on the punctured disk. So we now have an orientation on the punctured disk of the determinant line. Great. How do we get a sign out of that? Well, we have another coarse orientation, and these are all in the notes, so you can look at it a little bit more carefully there, induced by the space of conformal automorphisms or variations, depending on how many punctures you have. Compare with this capping orientation. If they agree, plus sign. If they don't agree, minus sign. And that's the end of my talk. Thank you.
Okay, thank you very much. So, sorry, Catherine had to actually go run the teacher class, but are there any questions for Chindu?
Yeah, I have a question.
Yes.
When you in that example you drew with only 2 strands, was that a local picture or were you only considering 2 strands?
Do you mean the
cobordism?
This one?
Yeah.
Yeah, it's a local picture.
So how do you know if you don't do more dipping, how do you know that a chord far away doesn't map? How do you know it maps by the identity?
Well, that's what the dipping is for.
But
It's
then
to
you would have to dip the other strands as well, not just those 2, right?
Well, you sort of have like this cobordism box, right? The move is sort of happening only within this local picture, and outside we assume that it's going down by the identity. And so the mini dip then constrains the holomorphic disks in this local picture, and outside we only get trivial strips.
Okay, so you know that there's nothing else from outside going inside?
Right, yeah. It may be doing something going out to the inside on the differential, but not in the DGA map. So Casal's Ing gives an argument for what they're the one who introduced this mini dip process. They show how this localizes the DGA map there.
So it's a combinatorial argument. It's not an analytical argument that says there's no holomorphic curve starting from the cylindrical part of the cobordism and going into the non-cylindrical part of the cobordism. It's a purely combinatorial.
No, it actually limits the holomorphic disks, I believe.
Okay.
But yeah.
Okay, thanks.
The questions?
Chindu, in your abstract, you said that there are applications to non-orientable cobordisms. Could you say a little thing about that, maybe?
Right. So, okay. There's work by Rezhikov on how this sort of thing can be done in a non-orientable setting. Basically, for a non-orientable cobordism, you don't have a canonical choice of what sort of pin structure you might want to. So in that setting, we'd be working more with. But yeah, you don't have a canonical choice, as in the orientable case, of what sort of pin structure you might want to use. So in this case, we always have null cobordant. But for instance, yeah. So but there it might be Lie group. Sometime it might be null cobordant, depending on your cobordism. But what Rezhikov gives is basically a way to incorporate all the pin structures into the definition of the DGA map. And once you do that, I feel like there should be a way to apply this same argument then, going pin structure by pin structure to count the holomorphic disks, in sort of that, like, he does it in sort of like a sheafy way, but I think there's a way to actually get like a solid formula out of it. Yeah.
Cool, thanks.
I don't know that for sure, but I think that there's possibilities.
I have a question, but first, actually, I have a question on behalf of Catherine, if you don't mind.
Yeah.
So her question was, could you say more about the motivation of the mini dip picture, why we want to choose a chain map phi between those? Is it because your result then gives us information about decomposability and fillings?
Sorry, is the question concerning the mini dip part, or just why we care about saddle cobordisms at all?
I think the question was more about the motivation of the mini dip picture.
So the mini dip, the reason we mini dip it is just to make our DGA map easier over Z-mod 2, and that helps us to worry about less holomorphic disks when we're upgrading the Z. Then the reason that we then okay, so then the reason that from there, we can then use a mini dip picture by the appendix results in Casals Inc. to conclude the actual like theorem for any type of saddle cobordism. Right, so that sort of is like a combinatorial argument that shows that if this mini dip picture is a DGA map, then the induced DGA map on the side of the whole saddle cobordism has to be of a specific form. So then we know the entirety of the saddle cobordism picture. And the motivation for that is, right, yeah, fillings is a big example. So for instance, it was this theorem that it was using this thing that Casals Ing were able to construct a very different set of infinitely many fillings for certain Legendrian links, because in this integral lifted DGA map, there was you were able to use this to distinguish infinitely many fillings of certain Legendrian links using it. So, I mean, that's a big motivation. In general, I just find it interesting to coherently orient things. Yeah.
So maybe my follow-up question, maybe, so right, so you're saying there's examples where you have sort of two or even many fillings which induce different sign cobordism maps but induce the same map over Z-mod 2.
Yeah.
And is there some sort of easy kind of intuition for why, you know, how this phenomenon arises, how, you know, a situation where you have cobordism maps which all are sort of the same over Z-mod 2, but for some reason they induce different sign maps? Is there any kind of like easy way of, or, you know, kind of intuitive mechanism for this occurring, or?
Well, I mean, so one way of getting basically it's impossible to get like an infinite action on the Z-mod 2 version of the theory, right? Just because you only have finitely many things. So a priori, unless you're working with Laurent polynomials in the Z-mod 2 case, if you work with Laurent polynomials, you can distinguish infinitely many things. But if you're just working over the Z-mod things without Laurent polynomials, you just can't distinguish infinitely many things a priori, right? So does that make sense as to why we would, at the very least, need to work over Laurent polynomials or the Z version in order to be able to distinguish this stuff? Yeah.
I have one question.
Yeah.
Except the feelings found in the Casals-Eng paper, by finding the exact formula of the DGA map, do you get extra more feelings?
I don't know of examples outside of the Casals. Well, okay. Technically, there are other examples, but they build off the Casals-Eng examples. So there are examples in higher dimensions. I believe this is by Roman Golovko, if I'm remembering correctly. But these really build off Casals-Eng stuff. So as far as I know, no, not really. But yeah.
Okay, thanks.
Cool. Well, yeah, let's thank Chindu again for a great talk.